IT361 Module 1 Part 1. The first module comprises of graphs and subgraphs. First, we are going to see specifically graphs and symbol graphs, graph isomorphism. In mathematics, graph theory is the study of graphs, which are mathematical structures used to model pairwise relations between objects. Many real-world situations can conveniently be described by means of a diagram consisting of a set of points together with lines joining certain pairs of these points. For example, the points could represent people with lines joining pair of friends, or the points might be communication centers with lines representing communication links. Notice that in such diagrams, one is mainly interested in whether or not two given points are joined by a line. The manner in which they are joined is immaterial. A mathematical abstraction of situations of this type give rise to the concept of a graph. Now we can see how we can define a graph. A graph G is an ordered triple V of G, E of G, psi of G, consisting of a non-empty set V of G of vertices, a set E of G, disjoint from V of G of edges, and an incidence function psi G that associates with each edge of G an unordered pair of not necessarily distinct vertices of G. If E is an edge and U and V are vertices such that psi G minus UV, then E is said to join U and V. The vertices U and V are called the ends of E. We shall call its points vertices and its lines edges, as you can see it in the diagram. In the diagram, the vertices here are denoted as V1, V2, V3, V4 and V5, and the edges are usually, as we have discussed, it is denoted by lines, and here it is named in the figure as E1, E2, E3, E4, E5, E6, E7 and E8. So here V of G actually indicates the vertex set of G. So if you are considering specifically this figure, we can see how what will be V of G of this graph, what is E of G of this graph, and how we can define the psi G with respect to this graph. So with respect to this figure, V of G is the set. V of G actually indicates the vertex set of G, as we have named the vertices as V1, V2, V3, V4 and V5. Here V of G is equal to set V1, V2, V3, V4 and V5. Now E of G indicates the edge set of the given graph G. So here E of G is set E1, E2, E3, E4, E5, E6, E7 and E8. And now psi G is actually a mapping that associates the edges of a graph with its corresponding n vertices. If you are taking the edge E1 specifically in the diagram, you can see the edge E1, which is actually represented as a line in the figure, has got two n vertices, say V1 and V2. So corresponding to psi G, the image of E1 under psi G is actually its corresponding n vertices V1 and V2. That is why it is written as psi G of E1 is equal to V1, V2. Similarly, if you are observing the edge E2 in the figure, you can see its n vertices are respectively V2 and V3. Therefore, here psi G of E2 equal to V2, V3. In the same way, psi G of E3 is V3, V3. Psi G of E4 is equal to V3, V4 and so on. So, psi G is actually a mapping or function that associates each edges in the graph with an unordered pair of distinct, or it's not compulsory that the vertices, n vertices should be distinct. If you're taking the edge E3, its n vertices are actually V3, V3. So that is the n verses are not distinct here. So that's why in the definition it was given that not necessarily distinct. Sometimes it will not be distinct. That is usually in the cases of loops or certain edges having only single vertex as its n vertices, the corresponding vertices will not be distinct. So that's why SIG is a mapping that associate each edges in the graph to its unordered pair of n vertices. Graphs that have a diagram whose edges intersect only at their ends are called planar, since such graphs can be represented in the plane in a simple manner. The above example that we have discussed about a graph, that is actually as an example of a planar graph, because you have seen the edges present in that graph are intersecting only in the n vertices. None of them are intersecting in any other points in the edges other than the n vertices. So this is an example of a planar graph. An edge with identical ends is called a loop, and an edge with distinct ends is called as a link. A graph is finite if both its vertex set and edge set are finite. A graph is simple if it has no loops and no two of its links join the same pair of vertices. In this graph, the edge E3 is actually a loop because it has identical n vertices, namely V3. So edge E3 is actually a loop. Loop is also called as a self loop or symbol loop. But if you are considering E2, E2 is not a loop because it has two distinct n vertices, namely V2 and V3. So generally E2 is called as a link, or it is also simply called as an edge. So here in the graph, only E3 is the only loop present, and the other edges, say E2, E1, E5, E4, E6, E7 and E8 are actually links having distinct n vertices. Now this graph is a finite graph because you can see the set of vertices over here is finite in number, and the set of edges here is also finite in number. Hence this is an example of a finite graph. And talking about the symbol, whether this graph is simple or not. This graph is not simple because it contains a loop, say E3, and also there are two distinct two links which are having same n vertices, say E7 and E8. So this graph is not simple. So and we have already discussed that a graph is simple or if it has neither loops nor links with the distinct edges, with links having same n vertices. The links having same n vertices are also called as parallel edges. So in another way we can say that a graph is simple if it has no loops or parallel edges. Two graphs G and H are said to be isomorphic, which is symbolically written as G isomorphic to H if there are bijections. Bijections means a 1-1 onto mapping. Theta, here the mapping is defined as theta from vertex set of G to vertex set of H, and phi from edge set of G to edge set of H, such that psi G of E equal to UV if and only if psi H of phi of E equal to theta U into theta of V. Such a pair theta phi of mappings is called an isomorphism between G and H. To show that two graphs are isomorphic, one must indicate an isomorphism between them. That is, two graphs G and H are said to be isomorphic if there is a 1-to-1 correspondence between their vertices and between their edges such that their incidence relation is preserved. It can also be told that if the edge E is incident on the vertices V1 and V2 in capital G, then the corresponding edge E dash in H must be incident on the vertices V1 dash and V2 dash that corresponds to V1 and V2 respectively. So generally we can say two isomorphic graphs must have same number of vertices, same number of edges, and an equal number of vertices with a given degree. This is an example of two isomorphic graphs in which you can see the two graphs consist of 10 vertices and 15 edges. So they are preserving an isomorphism between the vertex set as well as the edge set because they are equal in number. In the first graph there are 10 vertices, and in the second graph also there are 10 vertices. In the first graph there are 15 edges, and similarly in the second graph there are also 15 edges, and their incidence relations is also preserved because as you can see each vertex in the graph is adjacent to near to three other. Each vertex has got three edges incident on it, and that is observed in both the graphs. So they are preserving the isomorphism. Next topics in this module are the incidence and adjacency matrices, subgraphs, and vertex degrees. First, we can see what are incidence and adjacency matrices. Two vertices are said to be adjacent if they are n vertices of the same edge. When a vertex VI is an n vertex of EJ, VI and EJ are said to be incident with each other. That's about the concepts relating to adjacent and incidence. To any graphs capital G, there corresponds a V by E matrix called the incident matrix of G. Let us denote the vertices of G B by V1, V2, etc. VV, and the edges by E1, E2, etc. up to EE. The incident matrix of G is a matrix. It is usually denoted by capital M of G, which is equal to matrix Mij, where Mij is the number of times 0, 1 or 2 that Vi and Ej are incident. The incidence matrix of a graph is just a different way of specifying the graph. Another matrix associated with G is the adjacency matrix. This is the V by V matrix, and it is usually denoted as A of G equal to matrix Aij, in which Aij is the number of edges joining Vi and Vj. Now we can see an example for incidence matrix as well as for adjacency matrix. A graph, its incidence matrix and its adjacency matrix are shown in the figure. As we have seen, the graph is given here, and first given is M of G, which indicates the incidence matrix of the graph. And we have discussed earlier that in this matrix, the rows is actually representing the vertices, and the columns corresponds to the edges. So if you're observing that incidence matrix, you can see 1 is denoted corresponding to V1 and E1 because the edge, you can see the corresponding Vi and the V1 and E1 are incident. That's why it is written there 1. Now V1 and E2 are incident. So corresponding to V1 and E2 there is 1, but V1 and V3 are not incident, so there is 0 there. V1 and E4 are also not incident, so there is 0. Similarly, V1 and V5 is incident, so there is 1 there. So from this matrix we will get an idea which all vertices are incident to which all edges, if they are indicates, and also how many times the vertices are incident on the edge corresponding edges. If you are observing the vertex V4 and the edge E6, you can see that The edge E6 is incident twice on V4 because the edge E6 is actually a loop on V4. That's why there is a number 2 denoted corresponding to V4 and E6. So this matrix gives the incidence of the edges with the vertices, and it is generally represented by capital M of the corresponding graph. Now, if you are observing the second matrix, as you can see, it is denoted as A of G, and you know A of G indicates the adjacency matrix. So, from this matrix, we will get an idea which all vertices are adjacent to which all vertices. So, obviously, here the rows as well as the columns are representing the vertices, and if you're and the digits in the matrix indicates how many times the corresponding vertices are adjacent to each other. If you're observing the first element in the matrix, it is 0, which is corresponding to V1 because V1 is not at all adjacent to V1 itself, so it is 0 there. But if you are observing the digit 2 corresponding to V1 and V2, as you can see in the graph, V1 and V2 are adjacent with respect to two edges. That's why say E1 and E2, that's why here the number digit indicated here is actually 2. Now, if you are observing the adjacency with respect to V1 and V3, here the digit given is 1, because if you are observing it in the graph, V1 is adjacent to V3 only through a single edge. That's why it is written 1 there. And similarly, the digits corresponding to the vertices indicates how many times the corresponding vertices are adjacent. So, and this adjacency matrix is generally denoted as A of G. Now, coming to the concept of subgraphs as well as degree of a vertex. Degree of a vertex in a graph. A graph H is a subgraph of G, written as H subset or equal to G, if vertex set of H is a subset of vertex set of G, and edge set of H is a subset of edge set of G, and psi H is the restriction of psi G to E of H. And psi G, we are familiar, psi G actually indicates a mapping which associates the edges of the graph with the corresponding n vertices, and so correspondingly psi H is also a mapping, but it restricts the psi G to the corresponding edges of the subgraph H. So this is the definition for a subgraph of a G. If you are viewing a graph is said to be a subgraph of G, if you are viewing in a vertex set way, it should be a subgraph to the main graph G. If you are viewing in the edge set way, it also should be a subgraph. It should be a subset to the edge set of G, and corresponding to the mapping of the subset H, subgraph H, that psi H should be a restriction of the mapping psi G to the edge set of H. Now, the degree, which is usually denoted as dg of a vertex V, it is denoted as dg of V, in G is the number of edges of G incident with V, and each loop is counting as 2 edges. If you're considering a graph given here in this particular example, you can see the degree, if you're counting the degree of each vertices, the degree of V1 is actually here, if you're counting, we just have to count the number of edges incident on V1, and as you can see, it is 4. So degree of V1, here it is 4. But if you are observing the degree of V4, you can see the number of edges here. There are 2 edges, say E5 and E4 incident on it, and also one loop is there, E6. So the total degree, the degree of V4 here is 4, because a loop actually constitutes 2 to the degree of a particular vertex. Hence here the degree of V4 is 4. Now we can consider an example where we have to prove that the number of vertices of odd degrees in a graph is always even. So odd degree means the vertices having degrees like 1, 3, 5, etc. odd numbers. And what we have to prove here, the number of vertices of odd degrees in a graph is always even. So for that purpose, for its proof, what we will do is that if a graph is given to you, we will partitions the total vertices in the graph into two sets, say V1 and V2, where V1 indicates the set of vertices with odd degree and V2 indicates the set of vertices with the even degree. Then we have to so here V1 indicates the vertices with odd degree, and what we have to prove here, the number of vertices of odd degree in a graph is always even. That means here, since V1 indicates a set of odd degree vertices, we have to prove that the cardinality of the set V1 is even. Now we know a concept that the number of the total degree of the vertices in a graph is always even. So based on that, generally we can write sigma v element of v, degree of v, equal to an even number, because we have seen that sigma v element of v, degree of v, is 2 times e, where e indicates the edge set of the graph. And so no matter whether e is even or odd, multiplying that number with 2 actually gives an even value. That's why sigma v element of v, degree of v, is generally considered as an even number. And we have already splitted the vertex set in the given graph into two sets, say V1 and V2. So this sigma V element of V, degree of V, can be written as it is equal to sigma V element of V1, degree of V, plus sigma V element of V2, degree of V. So we will get sigma V element of V1, degree of V, plus sigma V element of V2, degree of V, equal to even number. What we have to prove? We have to prove the cardinality of the V1 is an even number. So what we'll do is that we will take, and this we have already got the sum is equal to even. Now what about the sigma v element of v2 of degree of v? As we know, v2 indicates a set of all even degree vertices. So the sigma v element of v, if you are adding those even degree vertices, we are actually getting the sigma value also as even numbers. Even number. So hence in this equation, sigma v element of v2, degree of v, turns to be an even number, and it is equated to an even number. So that means we will get sigma v element of v1, degree of v, equal to even number minus an even number. That will surely be an even number. Hence we got sigma v element of v2, degree of v, is even. Then it will conclude that the cardinality is this. We got sigma v element of v1, degree of v is even. We know that v1 indicates the set of all odd degree vertices. So since the sum is equal to getting as even, each of the degree values are odd, but its sum is equal to even, indicates that the number of odd degree vertices should be equal to even. Then only it will end in an even number. It will end in the sum. It will end the sum as an even value. Hence we have proved the cardinality of v1 is even. Now moving to more further problems. These are some problems for your practice. Try to do it by yourself. So that's all from this part. Thank you.